Hello, everyone. Thank you for joining the senior thesis presentations in the Department of Earth and Atmospheric Sciences. This event was recorded on May 8, 2020, at our unprecedented WebEx teleconference. This wonderful event was attended by numerous current geology majors, PhD students, current and former faculty, and even some alumni of the geology program. So we were very glad to see everyone there. Because we had some problems recording the first minutes of our event, I'll start by introducing our three defenders, Chelsea Thibodeau, Dan Figatz, and Nolan Gamet. And they did great, as you shall see. Now they truly can call themselves 2020 CMU graduates. And I will start with Chelsea. She will give a presentation on the evaluation of the log-derived porosity of the Antrim Shale, Michigan Basin. As you know, Chelsea has been a very active leader of AIPG and a fierce researcher, really, mentored by Dr. Natalia Zakharova. They already gave some presentations at the National American Geophysical Union conference in 2018. Chelsea's really been an active leader of AIPG, but did you know that she actually transferred to the geology major after starting as a music major? In any case, again, I apologize for the small hiccup of the lack of recording the first few minutes. I will let you read the introduction, and then Chelsea's voice will take it from there. Thank you again for joining us.
Log quality, as you see, is another challenge with this formation, and we'll get into that in a little bit. So our favorite Michigan Basin, it is 80,000 square miles, and it overlays the North American Craton. And the Michigan Basin shows a transitional period from a carbonate sea to a classic depositional setting. And as we geologists are all aware, it does not outcrop very well, especially in the lower peninsula. We're covered by Pleistocene age glacial sediments, which gives Michigan its very interesting topography, right? But the Antrim Shale specifically is an upper Devonian to lower Mississippian age formation, and those classic sediments, those detrital sediments, come from the Acadian highlands. And something really special about the Antrim Shale is that it's a biogenic gas. So, thermogenic gas, you have your gas matured or cooked through heat and pressure processes, whereas biogenic gas, the gas is produced just by microbial processes. So, kerogen is important. It interbeds with,
Chelsea,
yeah.
I think we just lost your share screen. We're seeing you now. I mean, you're on a roll. It sounds great, but we want to see your slides too.
You are still the presenter, so it's all good.
Yeah, it's coming up.
There it is.
Coming back. Thank you.
Here we go. All right. So the Antrim Shale. Oh, gotta press Control L. The Antrim Shale interbeds with the Ellsworth Shale to the west, but we're not going to be talking about the Ellsworth Shale. We're only going to be talking about the Antrim. And then the current lab data shows that porosity values range in the single digits. So for our two producing members, the Lachine and the Norwood, their porosity values are 4% and 5% respectively, which are pretty low. So I'm going to talk about the members, and I'm going to go top to bottom, which is youngest to oldest. The first is the Upper Antrim. This is a black organic rich shale, and it interbeds with the Ellsworth to the west and does not produce gas. The next member is the Lachine. This is a gas-producing formation. It's a black shale similar to the Norwood, and it has pretty high gamma values, 126 to 441 API. And the two Two are the more clastic depositional setting members. The Paxton is more carbonate rich. This is from the intercontinental sea, and its grains are lighter in color, which represents more oxide conditions. And then below that is the other gas producing member, which is the Norwood, and it's a quartzose rich organic shale. So we want to better characterize the porosity and heterogeneity of the Antrim Shale. It's a continuous formation across the basin, but like I said, its pore structures and gas distribution is not continuous. And then we want to compare geophysical logging methods, particularly two methods, and are there pros and cons for them? Is one better than the other? And then we want to briefly compare these results to lab values. Did we get realistic porosity measurements? So realistic porosity is anything from 0 to 50%, but for this shale specifically, we want to find porosity values from within 0 to 30% porosity. So the first thing we did is we went onto the Michigan Department of Environment, Great Lakes, and Energy website, and Rachel Agarty in her petroleum class showed us this great website called GeoWebFace, and it's a database with a bunch of wells across the state, and it's great for anything, not just gas production or petroleum production, but other types of minerals as well. And on this website, you will find raster files, which are just like pictures. And what we had to do is take these pictures and calibrate them and trace over them so that we could get numeric values. So Neuralog is a digitizing software that we used, and the LAS files are the text files that we exported from that, and then we put those into Excel for computation. So here's just a table showing many of the wells that I had to sort through. There's a lot more wells than this for the Antrim Formation. As you can tell, there's a lot of wells, but there is not a lot of data. So we narrowed it down to 4 priority wells, and I have their permit numbers listed. We wanted to find wells that had the sonic logs that we were going to use and bulk density logs that we were going to use for our methods. And then here are just some of the files that I encountered, some of these raster files. So these are all with depth as the vertical axis. And for this image right here, you can see all these crazy wraparounds. So if you have, this was a gamma ray log, this one specifically. If you have gamma ray values that are higher, it'll just wrap right around. And that's pretty complicated when you're trying to digitize it by hand. You have to keep track of what backup curve you're on. This image right here, this is a poorly taken photo, really fuzzy. Some of these images were tilted, which made calibrating the grid that we traced off of pretty difficult. And then some of these records would have multiple curves, geophysical methods per log, and that's pretty typical, but when you're trying to trace it by hand, that can be really difficult to interpret. So the first thing we did was we took the gamma ray curves. We wanted to identify the members, and then more importantly, we wanted to find the volume of shale. And the volume of shale is an important shale correction that we use in our 2 porosity calculation methods. Our first method was bulk density, and these logs are typically labeled as RHOB. Bulk density is inherently related to porosity. If you want to find the bulk density of a material, you want to subtract the void spaces. The sonic, as you'll see when I have the equation slide, is pretty similar to the bulk density idea. We use the Wiley equation, and it's more preferable to use compressional sonic waves, but we only had P waves available, so we just went with that. And the reason why sonic works is that the velocity of the sonic wave changes as it passes through different materials with different properties. As I mentioned before, you're going to have kerogen in some of these pores, but we wanted to just look at 2 scenarios, a liquid such as a brine or a gas methane, and we want to see how bulk density and sonic reacts to those 2 scenarios. Curves that I digitized, and then Neuralog has a helpful formula to calculate the volume of shale just based off the minimum and maximum values that you have on your gamma ray curve. And we took these volume of shale curves, and we use those in our porosity calculations as a shale correction. So This is just showing how we derive the porosity from the density formula. And the bulk density is just averaging all of the components. And then showing how we factor in the shale correction into that. And the same method was used for the sonic log. So instead of density values for sonic, we use travel times. It's not like velocity, it's the inverse of velocity because we're looking at slowness. And then here's a table of the values that we chose for our matrix, shale, liquid, and gas values when doing these computations. It should be noted that these aren't the exact values that are going to be found at every well. These are just preliminary values that we chose. So first we wanted to see what shale correction actually did. And if you look, the blue lines are the uncorrected porosity values and the orange ones are the corrected porosity values. So typically uncorrected porosity would be higher than the corrected ones. And already see that we're not getting just those single range digits for porosity. We're getting anywhere from 10 to 30% porosity for black shales or 5 to 20% porosity for gray shales. So we did that for the liquid scenario first and then did that same exact idea for the gas scenario. The same method for the sonic, and already you can see that the sonic porosity method produces higher porosity results ranging from 0 to 50% or 0 to 45% for a different well. And there's lower lows and higher peaks, and they're more you can see more distinction between the members and their porosity values. So sonic is a pretty sensitive method. What's really interesting in the gas scenario, like I mentioned, the uncorrected porosity curve tends to be higher than the corrected one, but for some reason in the gas, the uncorrected porosity values were below 0, so we had to omit them, but you're still getting pretty high porosity values, and that should not be 105%, that should be 10%. But you're getting higher porosity values with the sonic method. How these two methods were sensitive to the different fluids. So if you look on this density curve, they're pretty similar to each other. You have the same peaks in the same spots. They pretty much match each other. But the sonic method, again, produces higher results and can have higher peaks and lower lows. So the sonic method is incredibly sensitive to the fluid that it's in or measuring. Want to compare again how these curves look to each other. Are they similar? For the sonic porosity in the gas scenario, you have a lot of crossing over of density produces higher porosity or sonic method produces higher porosity. So the density, if you look at this blue curve, the density of liquid, the density curve looks pretty consistent no matter what fluid you're in, but again, the sonic porosity, especially in gas, can produce different results. So sonic is pretty sensitive and the gas fluid tends to change that. And then we wanted to compare these again briefly to lab results. So did we fall within that realistic range of 0 to 30%? And with the exception of well 48772, we got higher porosity in that area, but we had these double-digit porosity values, and that is larger than what data from the Michigan Geological Repository had found, and their average porosity value was about 4.7. So there's something missing in there that we need to find when we want to look for these pore spaces. So the log-derived porosity of the ancient materials suggests that there's higher porosity values than what we get with those lab measurements. The reason for that is that lab measurements only measure the connected pore spaces. And if you're going to be producing gas from this formation, you're going to be opening up those pores anyway with fracking, hydraulic fracturing. The density method is more realistic and a more reliable method of measuring porosity. It's not as sensitive to the different fluids. But if you have the means to possibly go member by member and find out what fluids are present at each depth and the mineralogy at each depth, sonic may be a great tool if you want to get a more accurate representation of your porosity. So in future work, we want to better understand the mineral composition of the shale, and I would suggest on a member by member basis, since the members of the Antrim Formation are all fairly different. better understanding of what fluids are present. Importantly, adding organic matter and kerogen into that equation because kerogen has its own densities, its own travel times, and its own porosity structures. So here are my sources. And I want to acknowledge the Michigan Geological Repository for Research and Education. We worked with them in trying to collect all of our data and looking at average porosity values. They really helped us narrow down what data was available. I want to seriously thank all of the EAS faculty, whether you're currently teaching at CMU or not. All of you have been so impactful into my life. And also Tara, let's never forget Tara. And I want to give a special thank you to the birthday professor, Dr. Natalia Zakharova. She has always been so encouraging whatever I wanted to do. I feel like I just walked in and said, "This is what I want to do." And she was like, "Okay, go for it." So thank you, Natalia, for your encouragement, your support. You've been a really wonderful professor and a friend to me, and I really appreciate you.
Right. Questions. Woohoo! So, any questions for Chelsea?
Hey, Chelsea, I have a question. Can
Yeah.
you hear me? Yeah. How thick is the Antrim Shale?
It kind of varies, but it's about, I read like 1,700 feet thickness in sediments. It was kind of hard to find that, but it was about 1,700 feet in some spots.
I was wondering if you had to pay any attention um, to the direction that the wells you looked at were drilled in, because if any of them might be horizontal as opposed to vertical, would that have an influence on your analysis and your porosity?
I would definitely think that would have an influence. That's not something that we looked at, but that's super important to consider, especially hydraulic fracturing methods tend to be horizontal.
Depending on
But
the
I'll
age
just
of the
comment that
well.
actually, sorry, in Antrim, actually, most of the wells are still vertical. It doesn't.
Yeah, they're old.
They don't do this kind of traditional horizontal drilling. They do different types of stimulation and mostly through vertical wells. So those that Chelsea presented are vertical.
I'm seeing here a message from Kevin Jensen. He says, "Nice work, Chelsea. We found similar results in the Marcellus. Reconciling log and core porosity is quite a challenge."
Hello, Kevin. Thank you.
I would just like to make a comment that, firstly, excellent job, Chelsea. I love seeing you building on skills both from SEDSTRAT and petroleum geology. But this type of project is really what we would call, a job-ready type of skill, and that what you're doing is something that is a way to add value or to monetize assets that companies oftentimes look at. There's certainly wonderful new technologies, lots of fancy logs, and but a lot of times you just don't have that kind of luxury to work with the best of the best new data, and being able to comfortably go back and look at these older types of data sets and find value in older fields is a really important skill to have to be employable. So just commend you for learning some of the old stuff the hard way. There's no replacement for that.
Thank you so much. And thank you for the GeoWebFace webpage. That was so helpful.
Well, thank your
Any other
tax dollars.
questions?
That's part of the regulatory environment of the state of Michigan.
All right. So if there are no other questions, the next presenter is Dan Figatz. Larry, would you like to introduce your student?
I'd be happy to introduce Dan, although like Chelsea, Dan probably requires no introduction because he's been a tremendous leader in the geology student community. He has been a president of the Geology Club, or AIPG as we call it now. I'm very privileged to work with Dan. He actually started out, he's one of these students with many talents. He was working initially with Megan and doing some interesting lab work. Thanks, Dan, for your lab skills, which you've helped Leah continue her work with as well. But Dan's thesis took an interesting turn after Megan left, and he's now pursuing one of his other interests, which is sort of we would call arm-waving geology at the basin scale, a combination of tectonics and subsidence and all these things. So Dan's thesis is on a characterization of what he calls the sub-Kaskaskian unconformity in the Michigan Basin. With that, Dan, I'll turn it over to you.
Okay, so let me share my screen real quick. Okay, do you see everybody's face in there also, or just the presentation? Or do you see the PowerPoint slides?
We can see your PowerPoint slide.
Okay, thank you. Okay, so as I was introduced, my senior thesis project was on the characterization of the sub-Kaskaskian unconformity in the Michigan Basin. So the purpose of this was to I wanted to better understand the development of the Michigan Basin and what went into that. I wanted to look at what was missing from the rock record. Use that classic geology detective work to find some answers, to find out why the lithology changed across this boundary, and also just because I really like the Devonian. It's one of my favorite times in the Michigan geologic history. It's the age of fish. So, all right. Next. There we go. The geology of the Michigan Basin. So, it's an intracratonic sedimentary basin formed by thermotectonic subsidence during the Paleozoic. We're going to be looking at three specific formations of interest: the Bois Blanc, which is a Devonian in age, the Garten Island, which is also Devonian, and the Bass Island, which is late Silurian. And we're going to look at the boundary in between them, the subkaskaskian unconformity. So next I'll show you a cross section to get a little bit better of an idea. So this is a cross section of the Michigan Basin. This is the sequence boundary that I was researching. So fitting it into Sloss's supersequences. In this figure here, you can see these white and gray areas are depositioned across the North American craton from the west to the east. And then these black areas are non-deposition or erosion. So basically, this is where rocks are in supersequences laid across the whole basin, or sorry, the whole craton. And then these black spots are where the rocks aren't. And we're looking at this period of time, and this is the subkaskaskian unconformity that I planned on characterizing. So here is a stratigraphic column showing this. You can see the three formations that we're looking at. The Bois Blanc here overlays the Garden Island, which these two are separated from the Bass Islands by the subkaskaskian unconformity. So that gives you a good idea of where it is spatially. So the question here was, what caused this non-deposition? What caused there to be a 20 million year gap in deposition in this spot of the core? So my answer to this, my hypothesis was that a drop in eustatic sea level in combination with local tectonic uplift at the end of the Silurian generated the subkaskaskian unconformity. So I used three methods to try to answer this question. One, I looked at thermotectonic subsidence curves from a few different sources. Also looked at eustatic sea level curves to see if was the sea rising or falling during this time. And I also took this information and then observed in the core section what I saw to see if this data correlated. So here, this figure you see, this is a graph of subsidence versus age. And the Michigan Basin is this line that shows prominent subsidence. And as you can see, most of it was before 300,000 years ago in the Paleozoic. This blue line is the start of the subkaskaskian unconformities. So as you can see here, that there was continued subsidence over time, and then at this point, there was uplift. Or it's very small, but I measured it. There is an angle in this graph saying that it was uplift, and so then this orange line represents right in the middle, in between. This is the 20-year stretch, or 20 million year stretch. So here's the late Silurian rocks. On the other side would be the Devonian. And there was uplift, where these rocks would be eroded, followed by subsidence. So from the source, this chart also included the sea level changes, although I did look at other uh, graphs and they corroborated what I found here. That at this exact same time, there was also falling sea level. So you have ground going up, sea coming down, and that's a perfect mix for to make an erosional surface. So and then sea level rose, creating the later Devonian rocks of the Bois Blanc. So here is a map of oil and gas wells in the Michigan Basin. And so these are the two cores that I looked at. This one I looked at specifically, and this one I used as secondary evidence that Catherine Pollard described in 2013 in her master's thesis. So this one, the State Charlton 430, was from up in Otsego County. As you can see, there's a lot of oil and gas wells here, and they are drilling for Niagaran oil reefs, and which most of these, all of them are going to cross this subkaskaskian unconformity. But because this is an oil producing or anything I'm producing unconformity, it's understudied. Um, so it was a perfect opportunity for me to look at. So there's only 3 cores total, and I looked at 2 of them. So as for the State Charlton, going from bottom to top, at the base was anhydrite, um, separated, by some dolomite mud. And then for the entire Bass Island group, there was um, laminated mudstones that formed deep water sediments, and it was uniform for, like I said, the entire core almost. There was a few flakes, speckles of gypsum here and there, and some oil staining, but things were the same for a long time. And then suddenly there's this line here, a shift is where I think the contact is, because then it goes into a lighter colored, which could be weathering from being exposed or something. But the fossiliferous limestone here, there's some sort of mollusk or bivalves or something here. And this tested as limestone. I didn't have to scratch this at all to make it fizz with the hydrochloric acid. And then we get some bioturbations and maybe some mollusk shells here, and then another unconformity. So from here to here is the Garden Island Formation, and then it starts shifting into this cherty bioturbated limestone, and that's for the remainder of the core, which is the Bois Blanc Formation. So that here is the contact. The nature is pretty sudden. And in the Gregory #2 core, Catherine Pollard found close to the same thing, except the Garden Island Formation is not included in this core, but is deep water sediment, um, followed by contact. And then here's some bioturbation, and then in the rest of the core there was also more. So it was like what I saw in my core. And so then I took all this information that I described and I put it into this easy to read diagram. So bottom up, we had the anhydrite goes through until the Garden Island Formation, where you find some fossils and then bioturbation throughout. And then here is Bass Island Group dolomite, and then the Bois Blanc limestone and chert. This is their respective depths here. So this is actually deeper. So there was continued subsidence afterwards, and this was more towards the center of the basin. So it's been deformed since then. But I lined them up so that you could see uh, this is where the subgas cascade nonconformity is. And then so I compared this with eustatic sea level. And how I drew this into the chart was that I stretched it so that the right times where it would be on either side of this nonconformity, and I traced over it. So there's no ages for these formations, but I lined it up the best I could, and it shows that there is a fall in sea level during this time. And then I did the same thing for tectonic uplift, um, which shows that there was a high point uplift during this time. And there it is all laid out. So to evaluate the hypothesis uh, of subfast cascade nonconformity being caused by sea level fall combined with uplift was supported by my observations and through literature. There was indeed sea level fall, there was tectonic uplift, and the lithology of the cores support this data. That's all I have. So I'd like to give a special thanks to Dr. Lemke for picking me up and taking me on as my advisor, for his guidance, resources, and encouragement, all the people he hooked me up with and everything. To Dr. Megan Roberson for getting me inspired to take on a senior thesis, and also signing me in as a geology major at CMU here. So she was there day one, and she's here day last, whatever day it is. So thank you. Um, Thank you, Rachel Agardi, for being my sedimentology professor. Thank you for the materials that I used when I went down to the core repository to take my observations. It's a really neat table that we all used in sedimentology. If you haven't taken that class yet, you will soon, but it came in perfectly in handy, and it was so easy to read when I was compiling all this data together. So thank you, Mona, for your enthusiasm on my project, even though you weren't directly involved. After my proposal, she sent me papers related to what I was doing, like, oh, read up on this, read up on that. This will help you here, and so she was helpful from the sidelines too. Um, Thank you, Bill Harrison, down at the core repository for facilitating the cores and also the enthusiasm in the research. And just thank you, everybody at EAS, students and faculty. You're all really great people.
Yay! All right.
Thank you.
Any questions for Dan?
I had a question.
Yeah.
I was wondering if the unconformity shows up in other nearby basins, like the Illinois or the Appalachian.
I haven't looked into that, but it is something I'm interested in, and I'm actually going to be moving down towards the Illinois basin in Indianapolis. So, like, it's craton wide. So, if you go back to Sloss's super sequences here, um, it should be there in other basins. So if you take this framework and apply it to other basins on the North American craton, you should see non-deposition at this time from the Cordilleran to the Appalachian.
Yeah, that would be interesting to see how they compare across basins.
Yeah, it should be there according to sloths, but I have not looked into it perfectly or personally.
Hi, Dan. Excellent job. Just wanted to say I love seeing you all apply your knowledge from sedimentology and stratigraphy. And just want to let everyone know we had invited Dan to share his work and his findings with our class, and unfortunately weren't able to get that in before before our everyone's lives changed, basically. But
Yeah.
I'm going to take this recording and share it with my students. And I love to see all of you taking the things you learned and going out into the world with them.
Oh, thank you.
Nice job.
Thank you.
Dan,
Yeah,
I have
so
Oop, sorry.
go ahead.
Okay, quick question. When you compare two different wells, there were slight differences, right? Like one of them had the limestone. Do you have just any thoughts on, is it just the geographic difference, or there were slightly different conditions, or
I think that maybe it was at a different spot on the carbonate ramp, so it was showing different bases. So it like that location of these seems to be out farther towards the center of the basin. So um, in my paper, I have maps of the Devonian rocks, but um, in the Devonian and the Silurian, this would be more towards the deeper marine sediments. So there wasn't as much paratidal formations in the Gregory core, but there was a market difference.
okay, sounds good. And while we're in here, just a quick comment that the
Mhm.
Niagara reefs are those linear features that have green labels. The
Oh, okay.
the red cloud is actually antrim shale gas.
Antrim shale. I'm sorry. I.
Just a quick comment, but it doesn't matter. Great job.
Yeah. Imagine going after the Antrim shale and then messing that up. Like. Oh, but thank you.
Okay, mine's quick comment also. So congrats, Dan, on wrapping it up and taking this on from like a huge change. We were talking about a whole bunch of different
There was
ideas. So
paleobiology and like,
yeah,
yeah. No, I was.
yeah,
It was.
all
It
kinds
was
of different
cool.
things. So I'm really happy to see how you tackled a tricky set of questions. And and this is like a tough one in geology, right? The it's where you have the absence of evidence. And it's a chicken and egg too. Do we have absence of evidence for this reason or this reason? And it's probably both. And so this kind of approach where you're using both what's already known um, or expected from a general scale, but also looking at the details of how those records were put together
Hmm.
is like a valuable step in any progress we're going to make on those kinds of big, like you said, armchair questions in geology. So
Yeah.
way to dig in and give it a go. It's a challenge.
Yeah. Thank you.
So
Because I mean, the information's out there, but here's a nice tied together.
yeah,
Yeah.
yeah. And
With
another thing would
descriptions.
be
Yeah.
yeah, exactly. And another way to look at some of that interesting stuff would be more database mining, like MacroStrat and some of these tools where people have uploaded large quantities of at least formation level information. So exciting stuff. And then I had one more thing I was going to say. Yes. Oh, so thank you for being a geology major.
Yeah.
You
Thank
came
you.
in
No, I've
like,
had fun.
am I too old to be a geology major? Man.
I mean,
So
I don't know. I spent a lot of time working on my 2-year degree, so it was.
yeah, so you made it. You're there you go. You're
Yeah.
right. Thanks,
Thank you
Dan.
so much.
Congratulations.
All right.
Hey, Dan, can I ask
Um,
one more question?
Yeah.
Squeeze it in since we have so many SEDSTRAT students watching or soon to be watching.
Uh-huh.
How would you um, characterize each of those formations within a sequence stratigraphic framework now that you've looked at their faces and you know where they sit relative to that sequence boundary?
So, between the two that I looked at, the Bois Blanc formation, the Devonian formations, and the Silurian, like within, where is it? Right here.
Well, I'm thinking about what systems tracks they might represent.
Oh yeah. So um, you're going to have, at least with this, where you're getting um, these deep water sediments, that's going to be in like a high stand system tract where the sea level is high and you get high deposition, and then there's a relative fall where it transgresses, and then it goes into low stands, and where you're going to have erosion or non-deposition, and then of course then that regresses again, and it's a cycle, and you can almost see here how something like that. I mean, this is way more broad. Like every deposit on the North American craton isn't a sedimentary, deposit like this, but um, yeah, you can see that, like, for example, that it was a high stand here at the Bass Island. It goes into low stand. There's a period of high stand again that makes the Garden Island, and then there was another unconformity between the Garden Island and the Bass Island, so that could be another low stand that goes into there. So that's how these formations would fit into the high stand low stand framework.
Super. Thanks a lot.
Yeah, no problem.
All right. So let's move on to our last but not least presentation of the day, and we'll have Nolan Gamet. Um, just like the others, Nolan doesn't need much introduction. Everybody knows him being very active with AIPG. He's been the vice president of AIPG. He's been involved with leadership safari and so on. Well, he got to start to work on this project last summer, and his time, however, was very limited, trying to work on samples, start preparing samples at the same time, going on field camp or doing leadership safari and other activities. It's been a good start. And then he continued on and off, and you know how we got kicked out um, in before spring break, so some of the data didn't get completely analyzed. However, he did a wonderful job building on the previous study of Christina Doran. And so here we are adding a little more to the story about spodumene. The title of his talk today is Distribution of Trace Elements in Spodumene, Insights from Preliminary Cathodoluminescence, PXRF, and Scanning Electron Microscopy Results. So take it away from here. If we pass the ball to
I just did that, I believe.
oh, you got it? Okay.
Yeah.
Oh, okay, yes. Oh, I thought it was still Dan. Sorry. There we go.
No, I think I surrendered it.
Okay, it's all good. And we could hear your voice just fine. And your screen is coming up. Yes.
You see it?
Yes.
All right, like Mona said, my name is Nolan Gamet, and this is my senior thesis. It's like loading my. Okay, there it goes. Okay, to start off with the acknowledgements, I'd like to thank the whole entire faculty, my fellow colleagues, and especially Tara, who did hard work in the office. But especially give thanks to Dr. Mona Zabriskie for all her wonderful help and all the time she dedicated towards this project. Dr. Lemke for letting me use the portable X-ray fluorescence. Dr. Student for letting me use the laser ablation ion coupled plasma mass spectrometer. Dr. Oshel for scanning electron microscopy. And then my fellow colleagues Stefan, Christina, and Carly. This outline, I'll begin with the introduction, followed by previous research, the aims of my study, methods, results, conclusions, and then ending with future work. To begin with pegmatites, the pegmatite of this study was a lithium, cesium, tantalum pegmatite group, which is part of the rare element pegmatite class. These pegmatites are of economic importance because they're able to accommodate rare and trace metals in their structure. They have many industrial applications, including lithium for batteries, tantalum electronics, cesium for petroleum drilling processes, and they also contain collectible gemstones such as this kunzite sample. So pegmatites have unusual physical and chemical properties that allow them to accommodate these trace and rare elements in their structure. They are internally zoned, beginning from the wall zone inwards towards the core zone. They may contain crystals upwards of 14 meters in length, and then most of the minerals of lithium aluminum, that is, are found in the core and intermediate zones. The mineral of this study was spodumene. Spodumene is lithium aluminum silicate in a single chain. It is a clinopyroxene, which means it has two cleavage planes at 90-degree angles and two prominent growth faces at 100 and 010. Because it is single chain pyroxene, it accommodates transitional metals and trace elements within its chemical structure. The first pegmatite in the study was located in Tin Mountain from South Dakota. It is located in the center of the Proterozoic Harney P granite granite in the Black Hills of South Dakota. This inclined pipe-shaped pegmatite, as seen in this image on the right, is approximately 200 by 20 by 30 meters in extent, and this was historically mined for rubidium with an alkali feldspar, cesium with pollucite, and then lithium within spodumene, which were found in the core and second intermediate zones, as seen in this picture by QSM and AQS. The second of which is Pumego North Pegmatite, located in Maine. This is located on the north side of Pumego Mountain in Oxford County, Maine. Had a surface exposure of roughly 180,000 square meters, and the preliminary drilling revealed that the spodumene bearing zone was approximately 20 meters in thickness. And this is a newly discovered deposit of giant spodumene, as seen in this image on the right, with this little person next to this giant crystal. So here's an introduction of boundary layers. So boundary layers are chemically modified units of the crystal in which the buildup of incompatible elements is pushed to the crystal interface during growth. Incompatible elements are those elements that are rejected during the crystal growth and then are forced to within the chemical structure. As seen in this image, they start off being really low concentrations and then increase drastically towards the end of growth. And that's also seen in the snow, as we call it, the snowplow effect, in which they build up at this top up here, and then as the composition of magma changes, they're then incorporated into it. But their existence in nature is still controversial. So adding to previous research, Christina Duran and Dr. Mona Zerbescu used trace element compositional variations with the portable X-ray fluorescence to try optimizing and calibrating this method. With this data, they were able to recreate a first of its kind maps with samples of this size, roughly 30 centimeters by 30 centimeters. To make these maps, they used the PXRF counts, as seen here. But they still had two questions remaining. They tried to determine determine if the primary growth of spodumene was a result of a solid solution in the crystal, or and then they decided the causes of iron, tin, and magnesium anomalies, where they came from. To do this, we selected a thin section location on the sample TM17 that included one of these anomalies, along with the other cooler portions of the zone. The biggest aims of this study was to first try to determine and figure out why and how these giant crystals form. To do this, we investigated trace element distribution in the medium to giant sized spodumene, and then is the mimetic chemical signature overprinted by secondary alteration? And then do these chemical zones relate to crystallography? So if this is the case, the incompatible elements should increase in the outer growth zone, and the compatible elements should decrease in the outer growth zone. The second biggest aim of this study is the economic importance. So the rapid collection of PXRF data in the field would be of great importance to exploration companies because it could potentially save a lot of money. Because the purity of spodumene is decreased with the increase of trace elements such as iron and magnesium. And as seen in this picture over here, we have fellow colleague Stefan looking very happy next to this giant pegmatite crystal. The methods I included sample preparation, petrographic microscopy, CL, SEM, PXRF, and the data processing and plotting. For the sample preparation, I began with slabbing the crystals perpendicular to their c-axis. This is an example of the giant spodumene crystal from Tin Mountain that is roughly 30 centimeters in diameter. This is the medium spodumene crystal from Pumego North Pegmatite. After slabbing the crystals, I crystallographically oriented them based on cleavage planes and growth faces. Following that, I clearly washed and rinsed the samples to rid of any saw marks or any trace elements, contaminants, etc. For scanning electron microscopy, we use this to document and characterize the mineral inclusions in the polysilicon section chosen from TM17. Backscatter electrons were used for the high resolution imaging, and energy dispersive spectrum were used for chemical analysis to make the 2D maps. And then we use the Hitachi 3400N2 scanning electron microscope located in the CMU Biosciences building. For the pXRF, we use the Bruker Tracer 5i, which is this gun-looking machine over here that was attached to this in-house apparatus. So this device shoots electrons into the sample and it produces these spectra on this program called RTAX. And then these spectra were used to map the elemental compositions. The elements we chose are listed here, and we chose these elements because they were above the detection limits from the device. Prior to doing the PXRF tests, I overlaid a grid of 143 points, each spaced at equal increments of 5 millimeters to maximize the resolution of the final 2D images. Each increment was approximately 60 seconds long. For the data processing, like I said, the spectra was recorded in RTAX. They were normalized using the rhodium peaks seen here because of the high peaks. And we used rhodium because rhodium is present in the X-ray tube of the PXRF gun. To normalize these, we used the rhodium counts in ppm and then divided that by the counts or the photon counts. And then that following or the resulting value was then multiplied by the element of interest or photon counts. And then we used, or these elements that we used had low detection limits of like 1 to 10 ppm, as seen here, this small Gaussian curve. And that's why we also rated of rubidium, because the curve was so small and under detection limits. So for SEM and reflected light microscopy of the TM spodumene, as seen in this section location, we located the inclusions along fractures. With SEM, we were able to identify these minerals as cassiterite, as seen in this SEM picture, and then Bixbyite, which is a manganese iron oxide. And then also seen down here is a cassiterite crystal in reflected light and the cassiterite crystal in SEM. So the results from TM and PM were pretty straightforward. The PBM overall had lower concentrations of trace elements throughout the entire crystal. As seen here is this top TM sample. Iron ranged from around 1300 to 2300, whereas the iron for the PBM ranged from 1200 to 1500 or so, and that could be also carried on to the manganese, gallium, and tin. So based on these results, we were able to distinguish two distinct zones. First, we looked at the hand sample. You could see a distinct coloration of white on this outer rim we called zone 2, and zone 1, which is more dark and gemmy colored. We were then able to add these zones using the tin map of on Abel, in which zone 1 had very high counts and zone 2 had low counts. These zones were also drawn in that are parallel to either cleavage planes or growth zones, but it was still unknown whether they were primary or secondary, which formed these zones. These zones were then also carried on to iron, magnesium, gallium, and germanium, in which iron and gallium, seen on the left, displayed similar variations compared to tin, and magnesium and germanium were almost opposite, in which they mostly contained low counts in zone 1 and high counts in zone 2. Furthermore, we constructed histograms which showed that iron and tin had more negatively skewed distributions, in which we then determined that zone 2 had the lower counts and zone 1 had the higher counts, as seen in iron and tin. And then manganese was more of a normal or Gaussian distribution, and it was harder to determine the zone differentiation because it was more randomly spread around the crystal. We then constructed scatter plots that also show this similarities, in which iron and tin had a positive correlation, and this can also be seen with the low counts in zone 2 and high counts in zone 1. This can be seen across all the maps, including tin versus manganese, manganese versus iron, and germanium versus tin, in which zone 2 had the lower counts and zone 1 had the higher counts. So as the proposed model talked about in the beginning of the incompatible behavior or the snowplow effect, the manganese and germanium had this behavior. So because the high counts were in zone 1 and the low counts in zone 2, this is explained as the composition of crystal changed. They were pushed along until they were finally forced to crystallize, or finally forced to become a part of the crystal. Oppositely, or contrarily, iron, tin, and gallium represented a compatible behavior, as we call this the vacuum effect, in which they started off with high concentrations of compatible and then resulted in towards lower concentrations as the crystal grew. For conclusions, we identified the tin and manganese hotspot anomalies, as we call them, to be explained by mineral inclusions such as cassiterite and bixbyite along fractures and cleavage planes. The overall trace contents were lower in PBM when compared to the Tin Mountain. And then we converted some of these weight percents in iron oxides, in which Tin Mountain revealed to have 0.6 with a standard deviation of zero point 0.2, and PBN had iron oxide weight percent content of around 0.2 with a standard deviation of 0.01, almost 3 times lower. The chemical zoning from the Abel maps and seen in the other data statistics suggests that the evidence of boundary layer was preserved in the crystal structure and was not affected by secondary processes and alteration. While tin, iron, and gallium behaved compatibly, manganese and germanium behaved incompatibly. For further work, more lines of evidence are required. To do this, just more samples need to be tested to make sure this method works, to investigate the trace element contents, and then to apply this method in the field, as seen by Niels here shooting this spodumene, this freshly cleaved spodumene sample. And then that would therefore determine whether or not it'll be useful to save money for exploration companies in the future. Any questions?
Yay!
Nice job, Nolan. Hey, Nolan, I have a question for you.
Yeah,
Uh,
shoot
I'm,
away.
I'm curious. This makes a lot of sense the way you explained it, and I appreciate the presentation. The snowplow effect versus the what was the
Vacuum. Yeah.
Vacuum.
the vacuum effect. So you made a couple of cross plots of your different elements. Did you have one that showed a compatible element versus an incompatible element?
Yes. 1 second. So
Yeah,
germanium.
that last no, those
So
were the
right here,
cross
I
plots.
this
And
think
red
you are right
corner.
there. Yeah.
Yes,
Yeah.
right here. So germanium versus tin. So germanium was the one that was, forget my bad, was the incompatible, right? And tin was compatible, and that can be seen here. So like zone 2, which we're supposed to have the lower counts, or zone 2 had the high counts of germanium versus low counts in zone 1.
okay, that makes sense because I'm thinking you're going to have an inverse relationship where you have high concentrations of your incompatible element. You might have low concentrations of the compatible element and vice versa. And I think I kind of see that there. So very good. Thank you.
Actually, Nolan had some line or circle going, showing these trends, and I just had him take them off yesterday because it was too complicated. But yeah.
Kind of ties into the question I was going to ask, but also I want to say congratulations, Nolan. You also
Thank you.
survived the transition, so well
Oh
done.
yeah.
So I'm kind of curious about a couple of things, but one is whether this splitting of compatible and incompatible in this particular like fluid composition is something that people have observed elsewhere, or is this sort of peculiar to this particular situation? How does it fit in with what other people have done elsewhere?
So it does fit in with what people done elsewhere, but not to this extent. So most of these like boundary layer experiments were conducted on like microscopic scale, showing like small zones that were more distinct. Whereas this study shows like the medium to large scale, like I said, like 5 to 7 centimeters, all the way up to 30 centimeters in diameter, which is pretty crazy. What was the first part of the question again? My bad.
What was the main thing? Is if like geochemically it made sense with what's known about those elements in the context of this particular fluid chemistry?
Yeah, so I know studies by Dr. Sebescu show this as well, like I said, in the microscopic versions, but then not much has been done that we know of, at least within these like large or medium to large to giant sized crystals.
The follow-on then is, so if what you find is common and that's how these minerals are distributed, what are your advice to the, how does that then play out with mining companies? Are they going to just
Um,
specific
so
holes?
I mean, if you find giant samples like the one seen in the pictures at the start, like that big of scale, you could quickly grind away. Like Niels and Dr. Rescue were able to grind away sample. I showed in the beginning the same
Stefan
person
as
here to
well.
grind.
We're
Yeah,
doing
and
lots of
Stefan.
grinding, polishing the surface in the field.
Yeah, so they grinded away the surface on the field as seen like over here, and then they shot it with a PXRF, and then from that data you could see pretty much the based off the chemical analysis. So if the iron and manganese counts are really high compared to other locations, it wouldn't be as or feasible or costly to mine them because they'd be less pure, and it's harder to like in the metallurgy or metallurgy processes to separate the iron and magnesium from the lithium in the spodumene.
Any other questions for Nolan?
I have for maybe a quick one. So you mentioned the secondary alteration, Alan, right? So have you checked with that, or like, what are your thoughts on that? Are you just checking that there is no something else, or could this signal be in any way related? So sorry, I'm not a
Oh no,
geochemist or
you're
what's
good.
this, so that may be a stupid question, but
No
I
worries.
was wondering whether you've discussed that.
Yeah, so at first, based off the anomalies, we've thought of secondary alteration as like a solid solution process within the spodumene. But then, like when I constructed these plots, these scatter plots I'm showing here, it looked as if these zones were more primary because they were kept through like alteration and weathering processes, as well as the Pomego sample we collected. Um, did show signs of weathering and alteration, but the zones were still prominent based off these data. That kind of makes sense.
Yeah, okay. So I
So
guess you look at the alteration, it just didn't seem like this signal
yeah,
coincided.
so because like say with iron and tin as well, they were so like well correlated or nicely correlated through the two zones. If there were secondary processes or something, there should have been, or I think should have been like drastic changes. Like say if there was a complete change in secondary alteration, these would be a lot different clusters. Like say zone two would be way lower, and zone two would be or zone one would be distinctly different. Whereas this is more correlated, which kind of gives signs of primary growth.
Oh, I see. Yeah. Okay. Thank you.
Yep.
So in this sample from Lumbago, Maine, indeed the alteration and the trace element contents were low. However, in the other sample from South Dakota, that's where um, the previous study by Tina showed that actually lots of those bright spots, the hot spot anomalies of tin and manganese were caused by cassiterite and 6-biite, which, yeah, Nolan studied this. So he didn't want to commit to say, yeah, probably they are secondary because they are related to fractures. And we see the little fractures associated with the inclusions. So, yeah. But yeah, good job, Nolan. So, Carly, how about you? Would you like to ask a question? I saw you earlier
Um,
trying. This spodumene is your territory.
I know. Great job, Nolan. I'm so super impressed. Did you do much cathotoluminescence? Or was it?
Yeah, so I I did mention that at the beginning. We did do cathodoluminescence on this thin section here that we used for SEM, but it didn't show anything. Like it just showed really high signatures of bright orange colors, like no distinct differentiations of color. And then from your study, we kind of determined that was based off the high iron and manganese contents. Whereas
Okay,
such
cool.
as yeah, like a fellow student Jarrett also did this, and there was distinct like colors between orange and purple in his samples, but mine were just kind of bright orange and blinded you as you looked at them.
Right. Yeah, how exciting. Very cool. Thanks for the shout out. Glad you got some use out of my findings too. And yeah, great job overall. I yeah, enjoyed it.
Thank you.
Mhm.
Right. Excellent. So, any other questions? This is overwhelming to see so many people and so many of our former students like Carly and Joe Mohan. Joe, when did you graduate? Are you still here? Hi, Joe.
Hey, yeah, I graduated in 2014.
Oh, nice.
2014, and now you are a PhD student, right? Still,
Yep.
or are you done? So just, hey everyone, this is Joe Mohan. Probably I'm maybe Jim and Mercedes remember Joe. And where are you now? Just a
I'm
quick.
at the University of Maine, so not too far from Plumbago Mountain.
Uh-huh. Hey, we can stay with you next time when we visit. Excellent. And of course, Kevin Jensen is a former student, and we still see him almost every day when school is in session because he's been teaching an introductory class with us. And I saw earlier Jason Oliveira. So that's great. That's great to see you guys. Thank you so much. This did become kind of a community, a reunion, which would have not probably be possible in the real setting in Brooks Hall. Yeah, I don't think Joe would have come from Maine all the way. So it's great to see you guys. And now I will grab, let's see, where is it? It's back with me. I will show the last slide here. Larry, would you like to introduce our list? I have a list here for you.
Oh, that's wonderful. Thanks, Mona. This is
That's me.
yeah, this is a banner year for our department in terms of geology graduates. We had several going out in the fall semester and several now. It's it's a bumper crop, as they say, and lots of very talented, dedicated, hardworking students. I, for one, am going to miss you guys. I've enjoyed having you in structure class and a few of you in hydro. I wish I could teach more classes as department chair, and so I'm envious of Mona and Rachel and Megan when she was here, Anthony, et cetera. Everybody who gets to interact with the students. It's one of the big privileges of our um, profession. And
And
I
Nicole's,
am,
they were in Nicole's class as well, some of them.
yeah, and Nikki and of course Natalia, all of us. All I can say is we're really going to miss you all, and we're proud of you. We know you're going to represent our department well as you go out into either industry or academia as you choose. Remember us, come back like some of the other alumni who joined us today. You're all part of a large family of geologists, geoscientists, earth scientists, and alumni of both CMU and our department. And I just want to say congratulations to everybody who's graduating, especially under these most challenging circumstances. You all deserve a huge celebration. I know it's going to be small, but at some point in the future, I hope you come back so that we can shake your hands, give you a hug, and maybe even go out for a beer afterward, like geologists do.
Yeah.
Sounds good to me.